Hi everyone, welcome to OPC Day. It's a pleasure for me to be here to speak today. My name is Jim Luth. I am a system architect for process automation R&D working for Schneider Electric, and I'm also the CTO of the OPC Foundation, where I also chair the OPCUA working group, a member of the TAC and the Technical Control Board. Today I'm going to talk about OPCUA systems and what I mean by systems as opposed to OPCUA components. So let's get into it. So in today's sessions, I will talk about what I mean by UA components and how that differs from what I mean by UA systems and how they're related. And we'll talk about global services, that is, services in an OPCUA system that have an advantage to be centralized. And most of my focus will be on what component authors need to do to take advantage of these optional global services. After we've discussed the services themselves and why you might use them and the advantage of having them centralized, I'll let you know where to find more information should you want to write a component that avails itself to these services, or if you want to write a central component to be the service itself. So by UA components, what I'm talking about are the UA clients and servers and sometimes publishers and subscribers that make up the applications in an OPC UA system. Any collection of such components in a particular place to do a particular task would be considered an OPC UA system. These OPC UA components are known in the OPC UA specifications as UA applications. I use the term components and applications here synonymously. The required behavior implied by the OPC UA specification largely centers around the interactions between these components, and hence OPC UA can be considered a decentralized architecture that doesn't rely on any centralized components. So this decentralized concept allows very small OPC UA systems to work easily without any burden of decentralized components. So as an example, let's assume that my OPC UA system consists of just this one OPC UA server, and I want to provide user access control to multiple clients that may be interacting with me. In a system like this, it's reasonable that the OPC UA server would store and maintain the username and passwords for all of the potential users of my server, and each time the check for the user and password would be done by the server. But if instead my UA system consisted of many servers and many clients and many publishers and many subscribers, that same system would be difficult to maintain without the use of some centralized components. So again, using the example of each server storing its own username and passwords for the same users becomes a maintenance nightmare for an administrator who has to keep everything in sync, adding and removing users, updating passwords, and so forth. So it's for this reason that we introduced the optional centralized components to aid in largely in the administration of OPC UA systems. So the first central concept we should talk about for OPC UA is the notion of discovery. Discovery allows one OPC UA application or component to discover other OPC UA components in the same system. Again, we use the term central or the notion of a system here to talk about the scope of discovery, and we're talking about, in this case, clients and servers discovering each other, or publishers discovering subscribers, or vice versa. The point here is that the concept of discovery is a global one. However, the default and provided mechanism for discovery that all OPCUA servers and clients must use is actually a decentralized, what we call ad hoc discovery mechanism. So this ad hoc discovery mechanism requires actually no centralized components and instead relies on local components and some multicast DNS to synchronize the different local components such that a system-wide, or at least in some cases, a subnet-wide discovery can occur. The ad hoc nature of the discovery has its advantages. Of course, having no central infrastructure or component required is a major one, but there are some limitations. In particular, we'll find that the broadcast messages used in multicast DNS don't always travel as far as you would like them to in the network, and there are some security implications. So OPC introduces the concept of a global directory service to overcome some of the limitations of the ad hoc discovery mechanisms. And in this case, the GDS, which can stand for Global Directory Service, or it can also imply a Global Directory Server, that is a central server that runs the Global Directory Service. And the GDS is really meant to be a centralized component where there are one or sometimes a few of them chained together in various ways, but nonetheless a centralized component that is in fact itself a full OPCUA server. And that is, it has a fully viewable address space, and it will read, write, and browse nodes and so forth, just like any other OPCUA server. But it has a specific information model with a specific object type called directory type, which in turn has its own set of methods, and these methods are used for doing directory type things. And it's the use of these services that imply that a client, be it a OPCUA server or an OPCUA client, that can take advantages of the features of the GDS itself. So let's take a look at the case of a GDS being used for server administration. For an OPCUA server to become known to the central GDS, the server itself needs to be registered with that GDS. And this starts to bring up one of the first advantages to using a GDS. That is, in the central server, every registered application has been validated by an administrator. So here, instead of seeing the OPCUA server register with the discovery server, as it does with the LDS in the ad hoc case, we see a server administrator using oftentimes a separate administration app to register on behalf of the OPCUA server the registration for the server. So again, one advantage to using the GDS in this case is that it's a trusted source for discovery as opposed to an ad hoc, somewhat untrusted source. So typically, of course, the server registration will happen during setup at some point in time, and that registration, of course, requires security of this server admin to allow this registration to occur. So clients use discovery servers, or the central discovery server, more or less for the same reason it would use the decentralized discovery mechanism, and that is to find registered servers in the system. But in the case of the central server, the client discovery mechanism uses a different method call, in this case query servers, to find the servers that it's interested in. And the query servers takes a different type of filter string than the typical server discovery with the ad hoc case. And thus the important thing to understand is a UA client while it requires to use ad hoc discovery, it does not require the use of the central discovery server. So to use the central discovery server, the UA client has to be written specifically to do so. And again, this is where the ability to use these centralized components becomes important, not just for people that write the centralized components, but for every OPCUA application developer, so that they understand that where these services are and why they would want to use them. So one of the interesting chicken and egg problems that arises for clients wishing to use a GDS is, how does the client find the GDS itself? And there are several mechanisms that can be used to aid in the discovery. One of the classics is that a good client would be able to be configured with the absolute address of a central GDS to be used, and therefore it's a manual configuration, typically of one endpoint for the one centralized GDS. However, a clever use of the ad hoc discovery mechanism in conjunction with the central server actually allows an alternate where the client discovery mechanism will first use the ad hoc discovery to find any available GDSs, and once it discovers GDSs, it, through the ad hoc mechanism, it will connect to the GDSs directly and then query those servers, query the GDS for the list of all other OPCUA servers. So again, in the case of discovery, OPCUA provides multiple mechanisms, and in many cases they can be chained together. So let's move on to our next centralized service, certificate management. As you probably know, OPCUA is heavily based on PKI, public key infrastructure, that is the use of X509 certificates that are used to identify both OPCUA servers and OPCUA clients. Since each OPCUA server instance and each OPCUA client instance in a system, of which of course there can be many, requires its own unique certificate, and certificates by their nature of how they're designed do not last forever, managing and updating and keeping the certificates correct in each of the clients and servers is a useful thing to do in a centralized manner. So in OPCUA, we've introduced the ability to have a centralized service, in this case the certificate management service of the GDS, and have it be responsible for managing the certificates for all the OPCUA applications. OPCUA interfaces are used between the GDS and the clients and servers in two different directions. A typical scenario is an OPCUA client will connect to a GDS and will pull its certificate from the GDS, because again, the client is the initiator of the communication and initiates, in this case, the pull action. A server, on the other hand, is a listening for connections, and in this case, the GDS acts as the client and often will push the certificate to the actual OPC server. And of course, in some cases, you can choose to use the other model if you have the reverse interface available to you, either way. And it's not just the initial certificate that's managed by the central administration here. The certificate renewal is managed so that when the certificate is about to expire, the client will pull and get a new certificate when it's ready, when the certificate is ready, the central certificate manager will push the new renewed certificate to the server. Additionally, the revocation lists that are necessary in order to properly do PKI when you have a certificate authority involved also need to be kept fresh and updated in the applications, and their certificate revocation lists are also managed in the same way, both with the push and the pull model. And lastly, the trust list. That is the list of certificates that a client should trust from servers, and the list of certificates from the clients that the server should trust is in authorization and connection activities are also can be managed through the central administration of certificate management. So in all these cases, as with the previous discussion about the GDS, for a client or a server to use the central administration for certificate management, it has to be built with that capability involved. We don't mandate the use of certificate management this way. Vendors can choose to implement certificate management however they want in OPCUA applications. However, it's strongly recommended that this mechanism using the certificate management interfaces of the GDS are used for this purpose. So the next key service that I want to talk about that's centralized is the key credential service. And first, let's talk about what a key credential is. So a key credential is a fancy name for a combination of a unique identifier and a secret that's used to access some service. A reasonable example of a key credential is a username and password. We're all familiar with those. But there are other fancier types of key credentials that aren't considered usernames and passwords, but they all involve an ID and a secret, and that's what we're talking about managing here. Where these come to be used in OPCUA, they can be used and managed in OPCUA for anything, but a typical example of where they're used is to access an authorization service, and we'll talk about authorization services a little bit later today, or a broker, i.e. an MQTT broker. So in PubSub, where we used MQTT as the middleware for the publishing, typically any entity that's going to access that broker, the broker service itself is secured, and the broker service will require some key credential to be passed to it in order to use it, and therefore the OPC publisher or subscriber would need to know that key credential. So by centralizing the management of the key credentials, again, I can update them and revise them and change them and present them and so forth in a centralized manner. So as you can see, the picture of the key credential management looks strikingly similar to the certificate management, and in fact there's a lot of parallels here. We have a push and a pull model, so clients typically will pull their key credentials from the central administration, and servers will typically have the key credentials for them pushed to them. And again, these are all managed it can be managed in a central location through the GDS, and can be fine-grained control over which particular applications get which particular credentials pulled or pushed to them. So the next centralized service I want to talk about is authorization services. And the authorization services are a way to separate concerns such that it allows OPCUA applications to delegate the user authentication and user management and assignment of users to roles to some external entity. And again, for example, an OAuth 2 server. And this decoupling makes it easier for administrators to manage users coming and going on the system, users' roles changing on the system without having to go to each and every OPCUA application and making changes based on those types of personnel changes. And this service, these services are also used, and I'll explain in a further slide how this might look, but we actually achieve a single sign-on in OPCUA systems. So let's take a look at the workflow for authorization. And I'm going to start in the middle here just to confuse you. But let's suppose a client here wants to read a value from a node in some OPCUA server. But that node and the value it wants to read is controlled with access control, and only certain people that are in certain roles are going to be allowed to access that particular value. So what has to happen in the flow here is the client uh, effectively connects to the centralized authorization service and presents its user identity token, whatever that is. It could be a username and a password. It could be something else that it already has. We'll talk about that in a minute. And with that user identity token, the authorization service will check the mapping rules that it has or that some underlying system might have and come up with an access token. And the access token is not too much different than the user identity token, except it very explicitly has the list of roles that are required or that are granted to that user based on what roles, knowledge of the roles the server will accept. Once it has that token, it will in turn use that token in its connection to the server and present that to the server and tell the server, I'm this user and these are the tokens I've been granted. At this point, the server will take the access tokens, validate them with the authorization service to be sure that the tokens are correct and real and make sense given the system. And then from the roles presented in the token, it will determine whether this node and the value and whatever operation is being done in that node is valid for that role. Okay, and so all these pieces here have to come to play, but at this point, the management of which users are in which role is not of concern to the server. All the server has to do is know which permissions he's assigned to the role to access the node. So again, the separation of concerns between what do I do in my controlled device with information, in this case the server, and what do I do globally in a system-wide basis in the authorization service. So let me explain now how this authorization service might be used in a more concrete example to provide the single sign-on that I said we could provide with this. So let's make the assumption in this case that we have a client, an OPC client that is running on Windows, and that Windows machine is in a domain, and the domain has Active Directory installed, and my GDS uses Active Directory as the authorization service, the back end of the authorization service. The GDS is the OPCUA component, the centralized component that's running the authorization service that's used as an intermediary so that the client and the server can talk to the GDS using OPCUA mechanisms, and they're shielded from the specific backend APIs for Active Directory. So in this case, the single sign-on happens quite nicely because the client, when the client before even the client starts up, the Windows machine has been started and the user, an Active Directory user, has logged into the machine. And so the user identity token that I need for this client is already present. So this step doesn't per se really happen. The client already has the user identity token that he needs because the machine has already been logged into by the user. So that token is passed to the authorization service, which in turn talks to Active Directory to get the roles that were assigned to that particular user, creating the access token with the roles. The client that takes the access with the token to the roles, the server collects those and then can make that assignment. So all of this happens without any server storing username and passwords, nobody having to log into the client application, the UA application, separate from the Windows login to the UA application, and essentially single sign-on is achieved in all of the clients and servers in the entire OPCUA system in this case. While I'm here, let me point out another common use in systems of the way that the services in a GDS are architected. The use here of a GDS and the authorization service as an intermediary between the OPC applications and the actual back end doing the work is a common theme. So in this case, I've used Active Directory as the OAuth 2 service providing the authorization on behalf of the GDS. The same thing is true, though, with certificate management. As an example, a CA and the services of a CA, a certificate authority, are often used as a separate back end to do the work of the GDS, as opposed to the GDS actually being the certificate manager. It's really just a go-between between a real certificate manager and the OPCUA applications. And the same can be true of any of the services provided by the GDS. The GDS may, in fact, just simply be an intermediary, and the real work is done in a separate subsystem. Another centralized concept recently developed for OPCUA is the notion of alias names. Through this mechanism, we allow a node in an OPCUA server to be associated with a user-defined name called an alias name. This alias name can then be used to look up the actual node, the ID or the address, if you will, on a system-wide basis. And this works much like a DNS server is used to resolve a domain name to an IP address. In our case, an alias server resolves an alias name to a node in an OPCUA server. So these names, as I said, are user defined. And again, a good example of that in process systems, typically on a PNID drawing, you'll see symbols like this. And this particular level controller here has been given a quote-unquote tag name called LIC 135. And although that doesn't seem very descriptive, throughout the plant, and no matter who you're talking to, LIC 135 uniquely identifies this instance of this controller in this loop. And so it would be common that the tag name or the alias name for the tag is given the name LIC 135. But of course, it corresponds to some node with some node ID in an OPCUA server that otherwise wouldn't be able to be identified as LIC 135. So when the alias names feature is implemented centrally in a GDS, the registration of those alias names, the tag names and so forth from the underlying system can be done in several ways. The simplest way is that an administrator could configure a tag name directly in the GDS and then provide the link to the server endpoint and the node ID associated with that tag. So sort of the manual, I can configure the GDS to contain any tag name I needed to contain. However, there's another way to get the tag names to the GDS, and this again comes from the idea that the GDS is the central thing that all the servers register to. So the logic is that when a server registers with a GDS, the GDS can go to that server and periodically read and refresh its list of alias names that are already defined in the server itself. So the tree here of the nodes in the server are then combined and coalesced into the tree of alias names in the GDS. So the idea is now that each server could have its own locally assigned tag names that are available. So if I connect directly to the server, I can find the tags in its server, but separately or in addition, I can go to the global service here in the GDS, and here I can resolve all tag names in all of the servers in the system. and which of course is typically how clients will prefer to use it. So you go to the top level alias server. In this case, of course, the GDS is to be considered the top level server. And from there, I can do the queries and the resolution to resolve my tag names to find my actual nodes in the OPC servers. You'll notice here in the diagram we have more than just tag names shown, and the alias name concept can be used for things beyond tags and sort of the named nodes in OPC servers. One example of that is in PubSub. We use it to provide named topics for PubSub publishing and subscribing. So again, a similar feature where I may not know where I can get certain data, but I know what the data is called. And so if I know that I'm supposed to subscribe to boiler data, I can go look up the topic called boiler data, and now I get the information I need as to what I need to subscribe to receive that boiler data without knowing anything about the absolute locations, IP addresses, etc. of the publishers that might be sending out boiler data. And as with the previous services that we've looked at, clients and servers, publishers and subscribers, any of the OPCUA applications that want to make use of the alias name feature, they need to actually write code to support that. So a server would need to allow alias name assignments. Again, these are end user typically installed name assignments. These aren't something a vendor would use to assign names ahead of time. Typically their assignment is made by the end user, so the whole configuration of that would have to be supported. And of course you'd have to be able to support the tree that I showed in the previous slide with the alias names and grouped appropriately so that other clients and the GDS could update themselves with those alias names. Similarly, for a client to make use of alias names in the typical way it would do that. So as you can imagine today, when a client browses a node ID in a server and finds, usually with the user interface and the help of a human, the client will find the node of interest, and then it will save that, persist it, so that when it starts up at a later time, it knows to just connect to that server, read that node, subscribe to that node, and get the value. So normally a client will persist the endpoint and the node ID, or sometimes the endpoint and the browse path, in order to start up again and get back to where you were. I want to subscribe to the 5 things I'm interested in. I have to remember what those 5 things are, and usually what I'm remembering and persisting is the endpoint and node ID and or the endpoint browse path. In the case of using alias name, though, you don't persist either of those. The logic is I persist the alias name, right? The alias name is the name that's been given in the system, and I use the alias name to look up the endpoint and node ID each time when I go to connect, or each time that it might have changed. And there's also ways to register to learn when an alias name changes or its assignment changes. And so this whole mechanism to properly use alias names, again, doesn't come for free in OPCUA. The clients need to be written to actually make use of it. And the last centralized component that I want to talk about today is the security key server. So the security key server is an entity that's used strictly in the PubSub paradigm for OPCUA, and it's used to manage the keys used for signing and encrypting the messages sent from publishers to subscribers. And in OPCUA, the keys used for this are not the same types of keys that are used in the PKI for client server, in that they are shared keys and they're temporary. And by temporary, I mean each key is used for anywhere from a few minutes to a few hours temporary. So to keep a flow going between a publisher and a subscriber, the keys change in every few minutes or every few hours, and the publishers and subscribers need to be using the current and correct key. And to do that, both the subscribers and the publishers need to be in relatively constant communication with the security key server to obtain the latest set of keys. So this particular service can be implemented anywhere. It's often implemented directly in the publisher, such that you might not even think of the security key server as a centralized component, but that would be a mistake because it can be. But oftentimes a publisher will manage its own keys, so to speak. So the subscribers talk to the security key server in the publisher to renew their keys. But there are advantages to implementing the security key server as a central component as opposed to in the publisher. In particular, it allows a key to be used and managed in one place and be used by multiple publishers. And this can be an important feature in some organizations of publishers and subscribers. So this service again is one that the good news here is PubSub is set up in a way that when you attempt to find the security key server and the location of it, it's pretty much directs you to its location no matter where it is. But I didn't want to leave, so this one maybe is the only one you could say comes for free, as in when you're using the security key server, you almost don't have to do anything special to use its centralized security key server. But it is certainly important to understand that a GDS as an entity may easily be the system-wide security key server for a group of publishers and subscribers, and it's important to know that too is an example of a service that can be centralized. So as promised, I want to point you in the right direction to find more information about the centralized services I've talked about today. Hopefully, you'll consider building your OPCUA applications to use these services. I hope if you've already built OPC applications that don't use these services, you'll reconsider going back and enhancing your products to make use of these. The first four services we talked about, discovery, certificate management, key credential management, and authorization services, are actually described in a standard OPC 10,000-12, or what we refer to as Part 12 of the specification, discovery and global services. So that one should be easy to find. It has the word global services directly in it. And so that's most of what I talked about today, but not everything. The other two, alias names, has its own part. It's called Part 17, alias names. And there you'll find all the requirements for clients and servers to use alias names, plus how it's aggregated up into the global discovery server. And lastly, the security key service, as I said, is used strictly for PubSub, and that whole service and how it works is defined and described in the Part 14 PubSub part. Oh, and another way to get more information on some of the global services I talked about and introduced you to today is to attend tomorrow's OPC Day sessions, where our how-tos go into more depth on some topics, including some of them that you heard about here today. So thank you very much for joining me. I hope I've invigorated your desire to go and enhance existing OPCUA applications or write new ones that make full use of our global services.